this basic probability. So we're doing a bootstrap sample. And you have to know what a bootstrap sample is. So it's this sampling with replacement. So we have 100 data points, and we're drawing a sample with 100 points by taking these 100 data points and choosing from them over and over again. And we're just interested in data point number 1. What is the probability it's chosen at least once? And what do people say? Let's see if there's a consensus first. Let's do it with the labels hidden. Ooh, okay. Out of 21 people, 19 people said something. They said 1 minus 0.99 to the power 100. And that is the right answer. So very good for people who got that. It's not 100%. You might think it's 100% because the chance of it getting chosen any time is 1%, right? You have 100 data points. What's the chance you choose data point number 1? It is 1 over 100, or a 1% chance. So you have a 1% chance to choose it 100 times, and you're repeating this 100 times over and over again. So a 1% chance over and over again. But this is not a situation where the probabilities add. So you cannot add them. And the reason is you might choose this thing more than once. We want to know the probability it's chosen at least once. So the correct way to do it is to get this, and let me write, since most people got it, let me write it down somewhat quickly over here, right, is to look at the chance it's not chosen. So the probability it is data point number 1 is chosen at least once. You think of it as 1 minus the probability it is never chosen. Data point number 1 is never chosen. And what's the chance it's never chosen? Well, there's a 99% chance that it's never chosen in each draw. So when you pick the first point, there's a 99% chance it's not chosen. The second point, there's a 99% chance it's not chosen. What is the chance it's never chosen? It has to not get chosen 100 times in a row. That's 99% times 99%, 100 times. So it's this. So this is 100 draws. And so there's a 99% chance it has to happen 100 times in a row. 99% chance has to happen 100 times in a row. Okay, and that's the answer. So most people got it. I think most people know what's going on. Questions or comments about that one? So here is the next interesting thing, is this number is very suspiciously kind of, as you increase the number 100, in general, the answer is going to be 1 minus n minus 1 over n to the power n. So we did the case n equals 100, 99 over 100 to the power 100. But in general, with n points, it's n minus 1 over n to the n. And the interesting thing about this is as you make n bigger and bigger, this quantity seems to get close to something. Let me show you what I mean in my favorite graphing calculator, Desmos. So here I have the plot of the graph. Let's make it match what I wrote down on paper. X minus 1 over x to the power x, because everything is called x in Desmos. And if you change the axes a little bit, let's make the y-axis go, say, from 0 to 3. I guess 0 to 1. And let's make the x-axis go from 0 to 100. So you can see, when you pick like 5 points, it's something, but then it gets very close to this magical number. It's not changing much. It's almost flat. It's converging to something. This is how you would say it in a calculus class. This quantity is converging to some number. And now the question for you is, what is the number? What is the number? Gets close to something. Okay, what is that something? I'm curious if you guys know. Think about it for a minute. I'll open up a little thing. I'll make a little word cloud. You guys can put in what you think. But take a minute and think of, what is this getting close to? In other words, what is the limit as n goes to infinity of this thing? Okay, take a minute. I'll make a word cloud in our poll, and then I will see who got it right. Okay. Okay, there you go. It's all set up. If you can recognize this limit, that means you had a very good calculus class. If you don't recognize this limit, you missed out in calculus class on learning a cool fact. Let me write it a different way. Okay, and you can put in "I don't know" as your answer. If you don't recognize this limit, it's a pretty tough one to figure out. So if you don't see it, put in "I don't know." Yeah, I'll show you the thing. Let me give one more minute, and let me show the formula. So here, you stare at the formula. If you don't know, if you don't recognize it, it'll be tough to get. So it's really just, do you recognize this limit? Yeah, I'll give a slightly different hint. What is 1 plus 1 over n related to this? Okay, time's almost up. Put in "I don't know" if you have no idea. I'm curious who's seen it and who hasn't seen it. If you do know, or you know what it's related to, put that in, and we'll see. Okay, one or two people left. I'm pressing the button. You must enter. Okay, let's see. What did people say? I don't know. Everybody does know. Wonderful. You guys are all going to learn something magical today. Okay, did anybody put in the secret special word? One person got it. 1 minus 1 over e. What? 1 minus 1 over e. That's what it is. Y equals 1 minus 1 over e. This thing is converging to a magical number, 63%, which comes from 1 minus 1 over e. Why is it converging to 1 minus 1 over e? Well, the definition of e is this limit. This limit as n goes to infinity. This thing is e. Who's seen that one before? E. Maybe you saw it and you forgot. What's the definition of e? Why do we do this whenever we do ln? Why do we do ln and not log base 10? It's because e is a magical number that you must love and worship. Okay. You guys don't know about e? What's going on? Where did you do calculus class? What did they tell you about e?
Remove the exponents and add log.
Remove the exponent and add log. Okay. All right. So I don't know who told you guys about e, but this is the definition of e. This is where e comes from. And e is, e is an important number. One reason e is important because the derivative of e to the x is itself. Okay. And the derivative being itself is related to this limit. It's all the same thing. Of course, a derivative is a type of limit. This is a limit. It's all related. Okay, that's e. So if you didn't know that about e, then you have no chance of getting this problem. But the upshot is if you do the limit as n goes to infinity of 1 minus 1 over n to the power n, that's the same thing as the limit as n goes to infinity of 1 over 1 minus 1 over n to the power negative n. And now you have the same thing with negatives. This is 1 over e. 1 over e. So if you put in a negative in the right spot, it comes in the exponent. So this one is e. This one is 1 over e. So what is the thing that we are looking at? It's exactly 1 minus 1 over e. So this thing that we want is getting close to 1 minus 1 over e, which is approximately 63%. Okay, so you'll see this quite a lot. What is the upshot of this, and why is this important? It's because I want you to know one fact. When you do bootstrapping for any reasonable sample size, so this is the most important fact that we're trying to get to right now, which is when you bootstrap with any reasonable sample size, when you bootstrap with n points and n is quote, large enough, you will do two things. You will sample approximately 63% of the points. So each point individually has a 63% chance. 63 is actually coming from this 1 minus 1 over e. Each individual point has a 63% chance of being chosen. In a sample of n points, how many unique guys will you get? It'll be 63% of the sample. So 0.63 times n points get chosen. And actually, this means that 1 over e points will not be chosen. Some points are never chosen. Are never chosen. How many points are never chosen? It's approximately 0.27n. And more accurately, it's a 1 over e fraction of the points. So when you bootstrap, you have n points, you're choosing them. Some of them get chosen more than once. Some of them get chosen 0 times. And the number that get chosen 0 times is approximately 27% of the thing. And that's where it comes from. So if you saw the videos, which I put up last week, then you will remember they reference in the videos approximately 70% or approximately 30%. Those were coming from 1 over e. So this is the fact that you must know. And what does large enough mean? We can look on the Desmos graph and see what large enough means. Large enough just means like anything larger than like 30, right? Like how big is the difference here? So it's already 63.8 and it goes down to 63.5. Like once you're at like 20 or 30 points, anything larger than that will be very, very close to this thing. Why is this interesting? These points that are never chosen, they are useful to us because we can use the points to test our error. So in traditional kind of cross-validation, you have a training set and a test set, and you sort of split it beforehand. When you do bootstrapping, you automatically get some points you never used, and you can use those points to measure your test set. So this leads, these points are useful, even though they are never chosen. Or I'll say can be useful, even though they are never chosen. And how are they useful? You can measure the error on them. So this is a definition of the OOB error, the OOB error. The OOB error is use the points, let's say the 27% of points not chosen. Use the 27% of points not chosen to measure the error. So just like you have a test set and a training set split in a bootstrap sample, you automatically get this OOB error. OOB stands for out of bootstrap or out of bag. You'll see why it's called out of bag sometimes, which is funny. Out of bootstrap or out of bag. We'll see where this bag word comes from in a minute. So you get an automatic train test split of just whichever points happen to not be chosen. There's almost always 27% of them. Use those points to test your error. And I'm going to show you an example of that in a second. But any questions or comments about that thing? Okay. Question here?
Yeah, I was going to ask, how do you identify those 27 points if you've created like 5 different samples of bootstraps?
Yes. So in every sample, every time you do one, you'll have a different set of points. And so you'll have a different test set for every bootstrap sample will have a different test set. So yeah, this is a little bit different than how you traditionally do things. Like in your projects, right at the very top, you say train test set, and they're separate, and then you do a bunch of work. In the bootstrapping, every time you make a new bootstrap sample, you get a new out-of-bag error, right? So every sample has its own test set, and every sample has its own test error, which means the error is going to move around. You're going to see this when I do the example. I'll show you the code that makes it and how it works. Yeah, great question. Anyone else? So let me show you bootstrapping on the world's simplest example, which is doing it for linear regression. So this is bootstrap for calculating some linear regression stuff. And so this is something we've seen a few times now, is we have a secret mean function, right? This blue function is not known to us. It's the secret function. We receive 10 training points that are taken from this secret mean function with some noise added. So this is like the cannonball problem, except for it's a straight line. And how am I going to analyze this? Well, so far we've done, you do take this whole thing and do linear regression. I'm going to show you how to do that with bootstrapping. So hopefully you guys understand the problem well enough that the bootstrapping part will be easy to understand. Okay, so here's what I want to do. Okay, this is what would happen if you just did straight linear regression. You take your 10 points and you just do linear regression, you get something, you get a beta hat 0 and a beta hat 1. The true answer is 2 and 3, by the way. So the secret mean function is a 2 and a 3. You got 2.08 and 2.94. So why would we do bootstrapping? We want to understand how far away are we from the true answer. So here, we are about 0.1 away from beta hat 0 and about 0.1 away from beta hat 1. We want to understand, find a way to mathematically show that with 10 data points, we get within 0.1. How do we do that? So here is how to do it. If you had 20 samples, of course in real life you only have one sample. So if we have 20 samples, then you can see that how far away you are typically. But here is how to do it with bootstrapping. So this is all from before. And now I'm going to show you the bootstrap. And in the bootstrapping, to figure out the out-of-bag error, I have this function called missing indices. And you'll see that I use this to calculate which ones were never selected in the bootstrap. So when I do bootstrapping, I choose a bunch of indices. I use the random.randint command, and that gives me numbers 0 to n, and I take n of them. So this gives me which numbers are you choosing? Are you choosing the first data point or the second data point? That's what I'm doing. And the bootstrap sample is my original sample where I extract the indices that I chose. So this is me choosing the bootstrap sample, and these are the missing indices. These are what are used for the out-of-bag error, or the OOB error. Let's add a little comment here. Yeah, okay, look, the autocorrect did it for me. Get indices for the OOB error, the out-of-bag or out-of-bootstrap error. And then what you do is you do exactly what I did before, but you only use the bootstrap sample to calculate the coefficients. So I get this beta hat 0, beta hat 1 from just the bootstrap sample, and that will give me many different samples of these beta hat 0, beta hat 1. So even though I only have one collection of points, I can get many different beta hat 0s and beta hat 1s. Here is what it looks like in beta space. Let me scroll down to here. So, right? So this plot, on the x-axis, I have beta 0. On the y-axis, I have beta 1. And the blue is the secret function we're looking for. That's exactly 2, 3. If we could get that exactly, we would be so happy. Unfortunately, we have a set of points that led to this red dot. So our sample, we got 10 points at random, which was this red dot. And we are not able to know the blue, right? We want to know how far away is the red from the blue. Well, every one of these skill points is a bootstrap sample from those 10 red points. So I had 10 points. I chose on average 6.7 of them, some of them repeated, to use in my bootstrap sample. And every time I did a linear regression, I get a different answer. And I can do this as many times as I want. So even though I only have one data set, I can kind of do it over and over again and get all these different things. And what you should recognize is that doing this bootstrap sample from our red sample is kind of like doing many samples, right? So this is a universe where we do many samples. You can't do that in real life because you only paid for one sample, but you can do bootstrap samples. And the point is the spread of the points somehow is about the same. So you can know about how far away things will be on average because you can see how much the variability is of the bootstrap samples. So that's what we did last time, and this is the main use of the bootstrap. I will write it down once again, is measuring variability. So, okay. Let's do a little reminder. Reminder. The main use of the bootstrap. The main use of the bootstrap estimate the variability, so how much things would change, ability of things. E.g., how much does beta 0 hat and beta hat 1 change beta based on our sample. And to maybe give a really super concrete example, without the bootstrap, this is, I think, the simplest way you can explain why anybody would do the bootstrap to a non-technical person. Without the bootstrap, you only have this, right? You just did it one time, you have this. So without the bootstrap, you say, I took my 10 data points, I got 2.08 and 2.94. So without the bootstrap, you say beta hat 0 equals 2.08, beta hat 1 equals 2.94. And with the bootstrap, what can you do? You can improve, instead of just telling me 2 points, you can tell me the 2 points and how spread out they are. So with the bootstrap, we can compute this kind of picture over here, and we can say, look, I ran the bootstrap sample, and most of the time, it's between 1.75 and 2.5. You can say that 95% of the time it's between these. So I could very realistically write down 2.08 plus minus 0.2. I can write that. So I can say beta hat 0 equals 2.08, and this is the new part, plus minus 0.2, and you can say 95% confidence interval. So this is what the bootstrap lets you do. Instead of just having 1 point, now you have a whole bunch of points, and you can calculate how much things are spreading out. This plus minus is the variability. And then if somebody says to you, okay, is the estimate you got, is it higher or lower than 2.1? You would say, no, it's not. It's about the same as 2.1. Here it seems like it's lower than 2.1. But the truth is, we don't actually know. We can only measure this to a precision of 0.2. So this is what the bootstrap lets you do. It lets you calculate this plus minus part. Similarly, for beta hat 1, you would get 2.94 plus minus, and I guess also about 0.2 because it's a square. That's the 95% confidence interval. And you can do this no matter how complicated your model is and no matter how bad you are at statistics, right? You just do the bootstrap. You draw this plot of all the different things you got, and then you make a square that contains 95% of the points. So very, very simple. That's what the bootstrap lets you do. This is all kind of review from last time. I'm going to show you the out-of-bag error in a second, which was the new part we did today. But any questions or comments about this thing? Okay. Let me show you the out-of-bag error. So here is the out-of-bag error. So what I did is, every time I did a bootstrap, I took out like 70% of the points and used them in my bootstrap sample, and 30% of the points were left behind. So you can calculate this out-of-bag root mean squared error. That's the blue histogram. So sometimes it was around 1. One time it was even like 2.4. And of course, in real life, we don't know the true error, which is in orange here. But the blue error is what you got. And you can see that it's sort of like estimating what happened. So the out-of-bag error is like the equivalent of the test error for the bootstrap. And you can use it to estimate the true error. You can make decisions like, let's try to minimize this out-of-bag error, just like in your projects you did the test error. So the out-of-bag is the equivalent of the test error for the bootstrap in some sense. So that's the new little bit. Any questions about that? So now I'm going to tell you a new definition. What does this word bag mean? What does this word bag mean? This is the new thing. We're going to learn something called bagging. Bagging, which is something you might hear. You've already heard about the out-of-bag error. Bagging. It has nothing to do with a bag. This is the most confusing thing. So you must remove the word bag, like in English, from your brain. Bagging is actually a compound word. It's a be something, ag something. Be ag. So bagging is be ag-ing. What is the be thing and what is the ag thing? Does anyone know?
Ag means aggregate.
Yeah, the ag stands for aggregate. 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 That's what the ag. Okay, I think if you got the aggregate part, probably based on the earlier part of the lecture, you can guess what the B stands for. What is it?
Bias.
Bias? Good guess. It is not bias. Okay. Anyone else? What B word have we been saying a lot? Bootstrap. That's what it is. Okay, so it is bootstrap. So bootstrap aggregation. So bootstrap. Okay. So bagging is using the bootstrap, and aggregation. Aggregation really means combining. This means combining. So what you're doing is you're combining your bootstrap samples to do something with them. Okay? So bagging is this operation. Let's combine our bootstrap things together. So this is like at the end of Power Rangers, where they all come together to make the big monster. Who watched Power Rangers as a kid? All right, this is great. Okay, so you know they all fight individually, but then the big bad comes at the end of the episode, and then they have to bag him. Okay, so that's how you remember it. Okay, so you combine the things, and I want to show you an example of this in the very simple linear regression case. So in the very simple linear regression case, remember we were trying to estimate the secret mean function. The teal lines here are our bootstrap samples. So we had our original 10 points, and I created this whole sea of bootstrap samples by selecting, subsets of them, and we got all these different blue things. So you have kind of like many different estimates. You have 100 different estimates for what's going on. One very simple thing you can do is average them. So average all these lines together. That's equivalent to let's average all the beta values, right? So instead of having all these different points, let's just average them together into one super point. And you'll notice something silly happens, right? If you average all these teal points, you just get back the red point. So in this case of linear regression, combining all the bootstrap models into one model doesn't really do anything. You just get back the original thing. So this is a kind of a silly non-example. In linear regression, bagging means you get a new model which has beta hat, let's call it our bag 0. That'll be 1 over n bootstraps times the sum from I equals 1 to n bootstraps beta hat bootstrap I 0. So you average together, every bootstrap sample gives you a parameter. If you average together those parameters, you get back the bagged thing. And here's the thing, because it's linear regression, this is actually very close to, this is approximately beta hat 0 of the original sample. So there's no point in doing this for linear regression because it's linear. Okay, and you might say, okay, well, why are you wasting my time telling me about this? The reason is bagging does nothing in linear regression, but it is extremely powerful for nonlinear things. And so we're going to learn some nonlinear stuff where bagging works extremely well, and it really like supercharges your models. So even though each model individually might kind of suck, when you bag them together, then they work better. So so the real example is in a nonlinear model. Bagging actually helps. Bagging can help. And that's what we're going to learn next. Okay? And what is the most nonlinear of nonlinear models? It is a tree. It is a tree. So that's what we're going to learn now. So we're going to example use trees. Okay. So that's what we're going to learn. Okay. And there was that video about trees. Hopefully you saw the video. But I'm going to explain a little bit how these trees work. And the trees, what they try to do is they just try to split the space of things into binary questions. So the goal in a tree, split the space, I'll say the input space, using binary. Binary here means yes, no questions. That's all it is. We're going to start, like I always do, with the world's simplest example, which is a dice roll. Okay? So let's imagine that let's imagine that we are rolling a dice, So we only have an X, and let's say it's a dice roll. Let's make it fun. A 100-sided dice. Okay? And here is your goal. I roll the dice. It's going to be a number between 1 and 100, 1 to 100. And you have to ask me yes or no questions until you figure out the value of the dice. Okay? And your goal is to minimize the number of questions. That's to kind of make the tree as efficient as possible. So probably you don't want to ask me, is it 1, is it 2, is it 3? You can probably come up with some better questions to ask. Okay? And for you, I have my very first little thing here is, can you guys figure out what it is? The dice roll question. So here we go. I'm thinking of a number 1 to 100 chosen by a fair dice roll. If you want to find my number in the minimum number of guesses, what is the best value to ask? And I phrase it as, is your number less than or equal to blank? And I want you to put in the blank. And also for fun, I brought in a real life 100-sided dice. You might think that's a golf ball, but it's not. It is a 100-sided. So I will roll it over here and secretly show you. You guys put in the thing and I'll tell you yes or no, okay? So I need like a box to like cover it from the front row over here. Here we go. It rolled off the edge. Okay, we got it. Okay, so whenever you guys are ready, put in what you want the question to be, and I will tell you the answer. Okay, 30 seconds left. Put in your guesses of what to ask me about this dice. And if you understand how this works, you will understand like vaguely how the trees work, right? The trees do exactly this. They figure out what is the best question to ask, and then they do that. Okay, final guesses if you haven't put it in yet. And let's see what people said. I'll have to zoom out or something. 18 people said 50. Great question. So what we're doing is we're creating a tree where the first question is, here's our tree. We say, is your number less than or equal to 50? Question mark. Is x less than or equal to 50? And then you kind of need to decide what to do in both cases, no or yes. I will tell you, in this case, the answer was yes. It was less than or equal to 50. So now you can ask another question. Another question. I think since so many people got it, presumably, you guys would ask me, if you know it's less than 50, probably your next question is going to be, is x less than or equal to 25? And then that's going to split the world into two more things, right? Similarly, if it was not less than 50, you would probably say, is x less than or equal to 75? Yes, no. So what we're doing here is we're creating a sort of sequence of questions we're going to ask about the value, and we're trying to do it in the most efficient way possible, where we kind of narrow down what is going on as much as we can. Okay? In this situation, there's only an x, but you could imagine that there's different things. Like you're asking questions about the x to learn something about the y. I'll show you an example in a second. But in this situation, I think you guys all figured it out. The best thing to do here is this kind of like binary search. Like this is the best thing you can do. This is called binary search. Binary search, where you're sort of splitting the search space into two every time, right? So instead of having possibilities 1 to 100, you split it into 1 to 50 and 51 to 100, and you keep splitting by 2 every time. In our case, let's see, if I turn this on. Is it going to work? Oh, these are very fancy. They used to be very old and crappy. Oh, wow. What is it? Oh, it just says visual presenter. Maybe I have to press a button. Ah, okay, yeah, you can see it. It was 38. Okay, so how many questions would you need? You need the size of this tree, which is log base 2 of the number of possibilities. So the number of questions is the log base 2 of 100, and then you would eventually get it down to just 38. I guess the log base 2 of 100 is approximately 6? 7. Okay, let's go with 7. Okay, so you need about 7 questions to do this thing, binary search. Yeah?
So if the answer is 38 and another is where x is not greater than, less than equal to 25.
Right, okay, yeah, so I guess you
have
have...
the next question I will ask.
Well, it depends if the answer is yes or no. I guess in this case the answer was no.
Yeah.
So you know it's between 25 and 50, right? So you know that it's not less than 25. You know that it is less than 50. So you know that it's between 25 and 50. So the next question you would ask is you'd say, is x less than or equal to 25 plus 50 divided by 2? Right? So we're sort of narrowing it down. When we started, x could be anything between 1 and 100. And then over here, we know it's anything between 51 to 100, right? Sorry, this is 1 to 50, and the other side is... This side is 51 to 100. And we're always taking the midpoint of the interval and splitting it that way, right? So in this situation, when we said no, we knew it was between 25 and 50, and you can further split that way. And this will get you there in the minimum number of steps because it's sort of like maximally using the space. All the branches are equally likely, and you have to go 7 branches deep until you get down to singletons. So that's binary search. I think you guys all figured out the 50. The rest of it is not too bad. Questions or comments about that? So now we're going to do it again, but we're going to make it harder, okay? So same thing, but harder. Dice roll question, but the dice are not even. So here I'm using a triangular distribution. So the probability of each number is proportional to its value. So what do I mean by that? I'm going to pick a number between 1 and 100, but I'm going to choose 80 4 times as much as 20. So the bigger the number is, the more likely I choose it. The number that I am most likely to choose is the number 100. I'm most likely to choose the number 100. How can you make this? Well, if you take 2 100-sided dice, and you roll both of them. So I'm going to roll both of them, and then I have to arrange it so they don't roll off the table. And I take the maximum of the 2 dice. So I have 2 numbers on there. My secret number is whichever number is bigger. And you see by picking whichever number is bigger, it makes the big numbers more likely, right? It's way more likely I pick 100 because there's a lot of different ways I could roll 2 dice where the bigger number is 100. It's extremely unlikely I would choose the number 1. The only way I choose the number 1 is if they were both 1. If I get 1 twice, then I pick 1. But if I get 100 with anything, I pick 100. So you can take 2 dice and take the maximum. This has a name in Dungeons and Dragons if you're interested. But now, same question. Let's make the tree for this guy, and it's no longer as simple as it was before. So I want you to think of what you should put. Is your number less than or equal to blank? And this time I gave you some different options to pick from. So you can click in there and see what the options are. I want you to think about it for a minute. How would you make your tree as optimal as possible? Okay, I will let you think for 1 minute about this problem. Okay, there's like 30 seconds left. If you know how to calculate it, go calculate. If you don't, pick at random or pick whatever you think is most likely, and we'll see where people end up. Okay, let's see what people said. What should you pick? Okay, so pretty even split here. 10 people picked 100 times 2/3. 8 people picked 100 times 1 over square root of 2. One of those two answers is correct, and they are both special things. 100 times 2/3 is something, and 100 times 1 over square root of 2 is something else about this triangular distribution. So let's draw a picture of the triangular distribution. You can kind of think about it as a histogram here, where there's x equals 1 all the way up to x equals 100, and the probability distribution is this triangle, right? So there's this, the like little thing here is 100 times taller, 100 times taller than the one over there, and it's making this triangle, okay? And somewhere in the middle here is x equals 50. That's sort of the midpoint in some sense. And there is these two special values. X equals 2/3 times 100. That's something some people picked. That's approximately 66. And there's x equals 1 over square root of 2 times 100, which is approximately 70. It's just a little bit higher. That's approximately 70. And these are two different things. That's one of them, 66 and 70. And they are two slightly different things. Which one is correct and why? Well, I guess first you have to tell me, what are they? So I wrote down the values, but what do they represent? Does anyone who voted for either one know which is which? Yeah.
So the 1 upon root 2 1 can represent the cumulative density function.
That's the cumulative. So to me, the cumulative density function is another function that looks like this. You take this thing and you add up the values. And what's going to happen is this thing is the derivative of that thing. So you have a function whose derivative is a straight line. That's a quadratic equation. So this one will look like this. This is the cumulative distribution function. And it ends at 1. So the probability at the end is 1. The probability at the beginning is 0. And it is doing a quadratic equation. So it looks like this. So that's what this looks like. This is the cumulative distribution function. Cumulative distribution. And it's the sum of the thing over there. It's a quadratic equation. You're right that this has something to do with it. What did you mean? It has something to do with that. I'll give you a hint. This is a quadratic equation. In fact, you can basically think of this as x squared, right? So, okay, it's not exactly the function x squared, because the function x squared ends at 10,000. This ends at 1. So it's really kind of like the function. It's proportional to x squared, but you can think of it as x squared. If this is x squared, what happens when you put in x equals 1 over square root of 2? Ignore the 100. Yeah, you would get a half. So if this is the quadratic equation x squared, then this point, x equals 1 over square root of 2. Let me use a different color. X equals 1 over square root of 2. X equals 1 over square root of 2, 100. That is exactly the point where it touches the halfway point. That's the probability. The cumulative probability is a half here. So this is a linear equation. This is a quadratic equation. And for a quadratic equation, this 1 over square root of 2 is exactly the point where the probability touches 1/2. What does it mean if it touches a half? It means half the time you are less than this, half the time you are more than this, right? The chance that you are less than 1 over square root of 2 times 100 is a half, and the chance that you are more is also a half. They're equal. There's a special name for that you learn in like grade 2. What is the name for the point where half the time you're less than, half the time you're bigger than?
Median?
The median, yes. This is the median. Okay, great. And now we've done the median a bunch of ways. Okay, if the purple one is the median, what's the orange one? What is the 2/3 times 100? That's the mean. Yeah, okay, great. Yeah. Okay. And lots of different ways to calculate the mean. You can kind of know the center of a triangle. So if you know your triangle centers, you'll recognize that 2/3. You can also do it with integration, right? If you integrate the function x squared, you get 1/3. So that's where the mean comes from. Which one do we want in this situation? Earlier in the course, we did some problems like this, and we wanted the mean, right? I made some specific arguments that explain why is the mean the best thing. In our situation, do we want the mean or do we want the median? Now that you know these two things, try to remember what we're doing, and let me revote, and let's see if we can break this tie. So half the people sort of picked the mean, half the people picked the median. Which one is right? Now you know which is which. Let me revote, okay? So let me give you one more minute to revote. Okay, I'm going to open this up, and I'll give you a minute. Okay, so essentially the question becomes, do we want the mean or the median? And I will just give, let's say 30 seconds here to choose between mean and median. Okay, 5 seconds left. Put in your guesses, mean or median. Okay, let's take a look at what people said. 19 people chose the median, and the median is the right answer. So if you chose the median, good job. Why is the median the best one? It's because it makes it so when we make our tree, if we make our tree is x less than or equal to the median, then we get a 50% split. So half the trees will go one way and half will go the other way. And this will ensure that we make our distribution as kind of as flat as possible. We sort of spread out as much as we can, and that will make sure that we need the minimum number of leaves, or the minimum number of layers, rather. The number of layers has a really funny name. If you do this exact splitting, what you get is the entropy of the distribution. The entropy, the number of layers you need. Number of layers is equal to the entropy of the distribution. The entropy of the x distribution. So if you do this optimally, you get the entropy, and it's measured in bits. Measured in bits. And so there's a whole field called information theory where they study these kinds of questions. And what we were really doing over here is maximizing the entropy. This is the 50% split is the maximum entropy choice. And that means make it as uncertain as you can in some sense. Maximum entropy choice. And so if you only have two outcomes, then you're going for this maximizing the entropy. And this is how trees are trained. So you guys have done this example now for the dice rolls. And in general, this is when you tell your computer, please find the tree, the computer is constantly doing these calculations. So in real life, you have some data set. So in practice, you have some data set. So you have your x1 and x2 values. And maybe you have some data points over here like this. Here the data points are like this. And what you try to do is you try to draw a line that maximizes the entropy. So you're saying, is x1, which x1 value should I ask about? Well, I want to make it split as entropy good as we can. And in our case, that was 50-50. In other cases, you might want to, if there's multiple classes, you'll see that means something else. But you're always maximizing the entropy. Maximize entropy. There's another coefficient people use sometimes called the Gini coefficient. The Gini coefficient. And that's another alternative, but same kind of idea. Try to get as much information as you can by asking questions that are right in the middle. You don't want to ask a question like, is it that point? It's not as good as narrowing it down. by a factor of 2. I'll show you a couple of real life examples of this. I'm going to start by showing you one from the table, from the textbook. Picture of a tree. Yeah, here it is. So it doesn't look like a tree. This is what the x1, x2 space looks like. And you see it's cut into a number of regions. Every time you ask a question, you make another cut. And so the tree actually looks like this. So first you ask, is x1 less than or equal to t? And then based on the answers, you ask about, is x2 less than t or x1 less than or equal to t over 3? And you create these regions of space. So by asking the right questions and trying to make them as information dense as possible, you end up with this. And your tree ends up being a function. This is a tree that outputs a number at the end. It outputs a number, R1, R2, R3, R4, R5. Those are the levels of the height. So the questions kind of divide the space into pieces. And this is answering what values are being taken there. And so this is from the textbook. This is an example of a tree. This tree is doing regression. So trees can do both regression and classification. So the value of the tree can be real value at the end of the tree. A number that's doing regression, or a class. Or a class, that's for classification. Okay, so this picture is a regression tree where it outputs a number, and you can see it sort of divides up the x1, x2 space and assigns a y value to each region, and hopefully these y values are close to your data values, right? So that's what a tree is doing. That's a regression tree. Let me show you a classification tree. And I copied this example from the Google developers course on random trees, which is very nice. And they have this new package called YDF. YDF stands for some crazy tree. But they have this nice penguins database where they have penguins. So there's many penguins. Every entry in the database is a penguin. You know, you can measure how long its bills are, how long its flipper is, how much it weighs, what year it was born, what island you found it on, and your goal is to classify which species it is. And there's 3 types of penguins. Here is a little tree that the computer made to classify these things. And it's nice because it shows you visually the distribution of the classes. So if you mouse over this, 41% of the penguins were this Adelaide class, 36% of the penguins were this Gen 2 class, and 20% of the penguins are this Chinstrap class. So that's the breakdown of our 243 penguins. They're split sort of into 3. And the very first question we ask, if you ask, is the flipper length in millimeters, is it greater than or equal to 207, you split the tree into 2 parts. You'll see that if the answer is yes, if they have a long flippers, these are penguins that are super floppy, almost all of them are Gen 2 penguins. So 95% split. On the other hand, if the answer is no, then it's like a 50-50 split, or I guess a 65-33 split between the other 2 classes, the Adelaide and the Chinstrap penguins. And when the computer was making the tree, it was saying, what question can I ask to make these things as separated as possible? So when can I get the most information to separate these 3 classes? And this is what it came up with. And there were 91, it also shows you the number, right? There were, of the 243 examples, 91 examples say yes, and 152 examples say no. So it's splitting into 2. So this is like another way to look at it, not looking at the XY space, but looking at the examples and how they split amongst the questions. For these ones, we ask one more question. How long is your bill? So first we ask how long your flippers are. Then we ask how long is your bill. And that almost perfectly splits them again. So we got 48% and 104. Not 48% and 104. 48 examples went this way. 104 examples went this way. And we have oh no, my dice. Okay. So here, there are 97% of them are Chinstrap, and 95% of them are Adelaide. So there's a kind of on a real life data set, there's what a tree looks like. You can also get, you take this tree, you feed it through a test set. So this was actually only on a training set. You feed it on a test set, and you can see that on the training set it was 95% accurate, but on the test set it was only 92% accurate. So this tree, even though it gets all the classes right, except for these small errors. You see there's like this little red bit and this little green bit. That's a training error. And there's a little green bit and red bit over here. Those are training errors. So the size of the training errors are just these little tiny slivers over here. And our training accuracy is very high, 95%, but our test accuracy is only 92%. And now the question is, how can we improve the trees to make them even better? So we've told you kind of what a tree is, which is not too complicated at the end of the day. It's asking these questions. And here's the problem with trees. The problem with trees. With trees is they not great accuracy. And in fact, I think the textbook has a nice little pros and cons list. Let me get out the pros and cons list of the thing. Yeah, let me open this up. Where are the trees? Yeah, this is the picture that I had. If you want to know the page on the textbook, it's page 335. I want the pros and the cons of trees. Tree-based methods, that's what the chapter we're in. And it has some pros and cons at some point over here. Pros and cons. Yeah, here they are. Advantages and disadvantages of tree. So they say trees are easy to explain, right? If you tell somebody I'm going to classify penguins by asking these 3 questions about the length of their flippers and bills, very nice. Some people believe that decision trees closely mirror human decision making. So it kind of is like how people think. They can be displayed graphically and are easily interpreted even by non-experts, especially if they are small. So that little tree I showed you with the penguins, if you were like a biologist in Antarctica measuring penguins, it's like easy to explain it to you, even though you don't know anything about stats. And they can handle qualitative predictors without the need to create dummy variables. So even you can ask a question about, is it this class or this class? You don't need to make dummy variables. They also can work with missing data, right? If you have missing data, you can have a rule for which way you go. But this is the thing that I said. Trees do not have the same level of predictive accuracy as other things. So one tree on its own is not great. And they are also non-robust. So they have high variance. A small change in the data will change the final tree. You can think of when you're choosing these boundaries, if you change a couple data points, it'll make the boundaries totally different. So these are the 2 kind of disadvantages. But fortunately, there is a way you can beef up your trees. How to make better trees. So not great accuracy. How to fix. And the answer is, one tree is kind of weak and not very good for accuracy, but many trees combined are very good. So use a forest. And a forest that means many trees. So many trees. So one tree individually is not very strong. It's easy to explain, but is not a very powerful function. It cannot represent things very well because it's sort of too simple. But many trees combined can represent something very complicated. So what we're going to do is combine many trees, and this is how I started the class. We're going to combine with bagging. Use bagging. Okay, and we're going to get to this in 1 second. This is a little bit like a situation where you want to have an expert who is really good at something, but you don't have an expert. You have a bunch of amateurs. Actually, why don't I bring up, there's a nice example in the Google course. Let me bring up this example. So this is from the Google course that is new this year on random forests. And they have a nice little plot here that I'm looking for of this thing. Okay, here's the classic example of this situation. Close this, agree to this. So a random forest, as it says right here, this is an ox. So here's the question. If you were an expert, you would look at that and go, that ox weighs exactly 1,287 pounds. But if you are not an expert, you could guess at how much it weighs, and you would be quite wrong. But the thing is, if you have many people who are quite wrong, you can combine their guesses to get something that's even better. And that is the idea of a random forest. Each individual tree sucks, but you combine them, and you get something better. So this is sometimes called the wisdom of the crowd. And it was this in 1906, there was a weight judging competition with 787 people. So most people were off by 40 pounds, but if you take the median of all the guesses, it's only 9 pounds away. So you go from an error of 3.5% to 0.7%. Some people, when they see 3% to 0.7%, they think, oh, that's only 2% better. You should think that is 4 times better, right? This number is 4 times bigger than this number. And so here is the plot. So here are the guesses at this competition in the 1700s, or what, not 1700s, 1906 with 787 people. And they guessed all sorts of things, and everybody spread out lots of bad guesses from all the individuals. But if you combine all the bad guesses, you get one good guess. That is the idea of a random forest. You take individual trees, which kind of suck, you combine them to make something better. And the way we're going to combine them is exactly what we did before with bagging. So the f function of the random forest, we literally average the values of x. We average over all the bootstrap samples. So we go sum I equals 1 to n bootstrap. And we do f hat tree I of x. So this technique of running many bootstrap samples and then combining them like this is called bagging. And each tree is trained, tree I is trained on bootstrap sample number I. So we take our data set, and by doing bootstrapping, we can retrain many different trees. Trees are very, they're very fickle. They change a lot. If you pick different points, you get a different tree. So the point is we're going to get many different, these things are going to be wildly different. F hat of tree number 1 and tree number 2 are going to be totally different things. And individually, they're not great. But if you average them, just like in the contest, you will get a better answer. By the way, this averaging, this is for regression, right? This is for if it's regression, you can average them. If it's classification, you can just take the majority vote, right? So this is random forest regression. And for classification, you take the majority vote. So equals majority vote. So instead of averaging the numbers, if 50% of the trees say it's a Gen 2 penguin, then they win the vote, and that's what you say it is. What this does is it takes the functions, which before were these like axis-aligned things, and it can make all sorts of different functions. And I want to show you an example of that. So this is, again, from the course at Google, random forests. So I highly recommend this new course if you want to get into this stuff even more. So here is an example where you have x1 and x2, and we're classifying points as either red or blue. And the real answer is that there's a red sort of circle in the middle. If you do any kind of tree, a tree is always doing divisions along the lines, like we saw before. So a tree will ask, is x1 bigger than this much? Is x2 less than this much? So trees can only ask questions about sort of straight lines. So that's a tree can't really get a circle very well. But if our random forest is a combination of trees, by combining the trees, you can sort of get these lines, these diagonal lines a little bit better. So a random forest is better than tree because it can do sort of arbitrary shapes by combining shapes of many angles. And I want to show you, as the very last thing, in the real life example with the penguins. So one tree, this was the best tree we could find, had a test accuracy of 92%. You should think of a test accuracy of 92% as an error rate of 8%. So 8% of the time we got it wrong. Let's ask, what would happen if we did a random forest? And so a random forest gets a test accuracy of 98.6. So same exact thing, same exact code. I just, instead of writing random tree, I write random forest. And it automatically does all this stuff. It computes lots of different trees using bootstrap samples. And it gets a test accuracy of 98.6. So that's an error rate of only 1.4. That's like 6 times better. So you should think of the reason random forests are so powerful is they like combine the best things about trees and they get rid of the worst things. There is one more thing that I did not say over here. So technically what I've written down, the tree I is trained on bootstrap sample I. There is one other detail that sometimes comes up, which is that we also, in addition to bootstrapping the data points, so having the samples, we also bootstrap the features and using random features. And they talk about this in the videos a fair bit. Instead of using all the different features that you have available, so if you have x1 and x2, sometimes you want to just take a subset of them. And by doing that, that makes them more independent. So this helps the trees be more independent. Helps the trees be more different. So that helps reduce some error in that it kind of makes the trees more independent. And by making them more independent, when you average them, you get something closer to the thing. So this is I think it has a name over here, which is, let me use the word that they use, attribute sampling. Let's bring this back. Where did it go? Here it is. So again, if you want to get into the stuff and learn a lot, this Google course is quite nice. It has a few examples. So we bootstrap the data points, but we also do this attribute sampling, where every individual tree is only allowed to use a subset of the samples. So here is a tree that is only allowed to look at features 2, 4, and 5. It is not allowed to use features 1 and 3. And you might think, okay, this is very silly. You're making your tree worse. But the point is it makes the trees more different so that when we aggregate them with bagging, we get a more accurate estimate. So it makes them kind of like more different and more independent, and that helps them work out. So here's a tree. First, it asks a question about feature 2. Then it asks about feature 4 or feature 3 over here. But it is never allowed to ask about features 2 and 5, and that's what makes it kind of a more unique. So it provides regularization. We're going to talk about regularization more in the course later. So that's attribute sampling. There's also bagging, is what we talked about before, bootstrap aggregation. That is splitting up the data set, and attribute sampling is splitting up the attributes. Random forests do both. Okay, so that's kind of all I wanted to say about random forests. Random forests will be one of the things you're allowed to use on your next project, project 2, which will be on classification. So you can use a random forest if you want for that project. Any questions or comments about random forests before we go? Yeah.
In the last meeting, you showed us
Yes.
the ground truth, the true decision tree, and then the random forest.
Yes.
What does it mean to have like a true decision?
Yes, this is a great question. So I didn't go into this detail. I told you how to make a decision tree, which is you repeatedly ask questions like, how do you split amongst this variable to split it as best as you can? It turns out sometimes when you do that, you get a tree that is kind of overfitting to the data a bit. So what you do is you go back at the end, after you make the decision tree, you do something called pruning, where you delete some of the questions. So you go back and you delete a little bit to make it a little bit less dependent on the training set. This is a little bit like when we did feature selection, right? So don't use everything, kind of go back a little bit. And yeah, I didn't get into it. If you want to watch the video, you can see how it does it. Yeah, great question. Okay, let's stop there. I'll see you guys on Wednesday. Don't forget to hand in your project before tomorrow evening.